Hello, everyone. I'm Sasha.
And I'm Amelia.
We work for the University of Massachusetts Lowell Human-Robot Interaction Lab. In our prior work, we have designed an assistive robot manipulator mounted to a mobility scooter, shown here. This work is focused on the implementation of a user interface that incorporates spatial augmented reality modalities using depth cameras and a projector. We are motivated by a desire to investigate how augmented reality can enhance communication and accessibility of our system.
In our earlier work, users designated objects for the arm to pick using a laser pointer. We demonstrated that the laser designation was robust enough for real-world use most of the time, but it had a few limitations, not only in robustness to varying surface reflectivity and lighting conditions, but in the amount of information that we could convey with just a laser pointer.
Our current system extends the capability of the previous laser-based object designation functionality. Using depth cameras and a projector, our system is capable of A. Direct selection of objects in the world by projecting a cursor into the workspace that the user manipulates with a joystick, B. Communicating which object the manipulator intends to pick, and C. Displaying the workspace of the manipulator. Our earlier approach involved detecting a physical laser dot using cameras. In contrast, our new system uses a virtual laser dot that is projected into the real world. This eliminates calibration errors and false negatives that may have occurred during the detection process in the previous system. Unlike the laser designation in our prior work, our SAR system can display symbols and shapes, highlight surfaces, write text in the environment, and vary its color and brightness.
In our system, visual information is projected into the world using a standard consumer projector mounted above the robot's workspace. To capture the environment, we have 5 depth cameras pointed towards the robot's workspace, mounted in different locations to make the system more robust to occlusions. The control panel has a joystick and 5 buttons, which can be individually lit up to convey which actions can be taken from a given state.
Here is an overview of the architecture of our projection mapping system. First, input is taken from 5 depth cameras mounted to the system surrounding the workspace of the manipulator. Then, using this captured geometry as a basis, some operation is performed, which can be any of those things in the processing square, to select areas of interest from the point cloud to be displayed. To project these areas of interest back into the real world, a 3D visualization is created and an image is rendered using a virtual camera placed in the same pose as the projector with the same intrinsics. The rendered image from this virtual camera is then displayed on the projector. Using the principle that a projector is simply the dual of a camera, points in the 3D visualization are projected back into the real environment. For further detail on how this system functions, please refer to our prior work.
Here is an overview of how object designation is performed using our system. First, the depth cameras capture a point cloud of the environment. Then, a ray is projected with the origin placed approximately near the user's head. The pitch and yaw of the origin of the ray can be controlled with the joystick. At some point, the ray intersects the point cloud, and the cursor is placed at the intersection of the ray and the point cloud, where a laser dot would be if it were a laser pointer. The rendered image containing only the cursor is displayed through the projector, placing the cursor in the real world.
The other SAR functions follow a similar pipeline, however, regions are highlighted based on different criteria. This is the intent communication. Our system uses a segmentation algorithm to identify and separate objects from surrounding surfaces and other objects in the point cloud. Once an object is identified, it is highlighted using green to communicate the robot's intent to pick this object. The user is then able to confirm or deny that this is the object that they want to select.
The system is also capable of displaying the workspace of the manipulator. In this image, surfaces highlighted in green are considered to be within the workspace and can be reached by the manipulator. The workspace is defined as all points within a fixed radius from the manipulator's base.
Here is a video of the system in action. The audio is muted, but voice prompts are guiding the user through using the interface. Here we can see the object designation as well as the workspace display. In the bottom right, you can see a visualization of the robot's perception of the workspace. The cursor is shown as a red dot which the user can manipulate using the joystick on the control panel on the top left. The workspace is shown in green, where the highlighted surfaces are within reach of the arm. Here you can see the intent communication. The user has designated this toy lobster, which is now highlighted in green. The robot is now picking the object designated by the user. We are currently working on a user study to validate our SAR-based system against a more traditional touchscreen-based graphical user interface. It is a within-subject study with two UI conditions, the SAR-based UI and the GUI, and two conditions with varying levels of clutter in the environment. We hypothesize that the SAR-based UI will be more robust to clutter. We also hypothesize that there is a relationship between a participant's spatial reasoning ability and their performance with or preference for each type of UI. Specifically, we expect to see a stronger relationship between spatial reasoning ability and performance with the GUI than for the SAR-based UI. If this is true, it could indicate that the SAR-based UI is more robust to varying spatial reasoning ability.
There are a few things we would still like to try with our system. Currently, the SAR UI gives an audio prompt to indicate when the system is thinking, but provides no active feedback, such as a loading wheel or progress bar. We would like to figure out how to implement some sort of scanning or thinking animation for the SAR UI. We are also developing methods to improve projector calibration to allow for faster, easier, and more accurate setup. And finally, we are investigating building a UI around a head-mounted display, HoloLens 2, as this may allow more flexibility in how we can design UI elements. Some things we'd love your input on are where might this sort of interface be useful, and what other features could a system like this perform?
Thank you, everyone.